Okay, welcome back to the deep dive. You hear it everywhere, right? AI, artificial intelligence. It feels like it's completely changing things, but what is intelligence, really? I mean, not just for machines, but, for us. So today, yeah, we're going to dig into that, peel back some layers. And our source for this is really foundational. It's an MIT OpenCourseWare lecture, a real masterclass, actually, in pulling out these, powerful but surprisingly simple ideas from AI.
Absolutely. And our mission today, well, it's to cut through all the noise, all the hype. We want to get to the core of what AI actually is. We'll look at its history, which is pretty fascinating, and maybe most importantly, figure out what makes this unique. Expect some, real aha moments, I think, and ideas you can maybe even use yourself.
Okay, so let's start with that really broad definition they give. AI involves thinking, perception, and action.
Yep.
Sounds simple enough on the surface.
It does, but there's so much packed in there. From the MIT engineering view, it's all about building models. Models specifically targeting thinking, perception, action. And this isn't just AI, you see. It's core to how MIT approaches, well, pretty much
Everything. Like what?
like uh, probabilities for machine learning, differential equations for, say, robotics, even how you structure stories in humanities to understand decisions. It's always about creating these mental models to explain or predict things. The lecturer even suggests that really engaging with AI concepts like this, it can actually make you smarter by sharpening your own models.
Wow, okay. Learning about AI makes us smarter. I like that angle. And key to building these models is representation, right?
Uh,
How you choose to represent the problem.
Exactly. It's critical. The way you represent something can basically determine if you can solve it at all. Think about the gyroscope example from the lecture.
Okay.
Many engineers might use that right-hand screw rule, you know the one?
Yeah, I think so. Kind
Okay.
of wave your hand around.
Right. But it often doesn't give you a real intuitive feel. The lecture suggests a different way. Just focus intensely, like with duct tape, on one tiny piece of the spinning wheel.
Okay, just one piece.
Yeah. And as that piece moves, say, over the top, imagine pushing it. You can feel which way it deflects, right? Apply that understanding piece by piece, and suddenly the whole gyroscope's weird behavior makes sense. It's intuitive. The simpler representation unlocked it.
That duct tape focus, that's a great mental image. It cuts through the complexity. So is a big part of intelligence, both human and artificial, just knowing what to ignore, what to simplify.
Precisely. Finding the essence. Look at the classic farmer, fox, goose, grain puzzle.
Oh, yeah, I remember that one. Get them across the river.
Right, without, anything getting eaten.
No.
A picture, useless. A
It's
poem, confusing.
But if you represent it by tracking who is on which side of the river, now you're getting somewhere.
Okay, so the location is the key representation. Yeah. 4 items, 2 locations each. That's 2 times 2 times 2 times 2. 16 possible situations or states. And the crucial thing is, a good representation, maybe drawing it out like a graph, it immediately exposes the constraints.
Constraints.
Yeah, it shows you the impossible situation. Like, you can't leave the fox and goose alone. It just rules them out visually. It's a bit like how algebra uses notation to show you what's possible or impossible in an equation.
Got it. So putting it all together, the big definition from the lecture is AI is about algorithms enabled by constraints exposed by representations that model targeted thinking, perception, and action.
Exactly. It's not just a definition. It's like a roadmap. It tells you AI's power isn't just raw computation. It's smart design. It's about crafting that internal worldview effectively.
Okay, so representation is huge. What about the actual problem-solving strategies? The lecture mentioned one that sounds almost too simple: generate and test.
It is simple, but incredibly powerful, and you use it all the time.
Yeah.
Think about identifying a tree leaf with a guidebook. You generate options by turning the pages, right? And you test each picture against your leaf until you find a match. That's it. A generator creating possibilities and a tester checking them.
Huh. Yeah, okay.
And a good generator, the source points out, doesn't keep giving you the same wrong answer,
Mm-hmm.
and it's informable.
Mm.
Meaning, if you know it's a deciduous tree, it stops showing you pine trees. It learns, gets more efficient.
That makes sense. Seems obvious, but yeah, it's everywhere. And this connects to the Rumpelstiltskin principle, the power of naming things.
Right, just having a name for something gives you power over it. Like knowing the plastic tip on your shoelace is an aglet.
An aglet, I actually know that one.
See? Now you can talk about its function, stopping fraying, making lacing easier. The name gives you a hook for that knowledge. And this leads to a really important point the lecturer makes: the difference between simple and trivial.
Ah,
Many huge ideas in AI, like generate and test, are profoundly simple. But sometimes they get dismissed as trivial because they aren't, wrapped in complex math. That's a mistake. Simple ideas are often the most powerful. Don't overlook them.
That's a fantastic point. We often equate complexity with value, don't we? Speaking of not overlooking things, we usually think of AI as like logic and symbols. But the lecture says we also solve problems with our eyes.
Yes, this is super insightful. It challenges that purely symbolic view. Consider this puzzle. Name the African countries on the equator.
Ah, okay. That's tough off the top of my head.
Exactly. But as I ask again, what happens in your head, you probably start to visualize a map, right? Your language system basically told your visual system, run a program, scan that map along the equator, count.
Yeah, I can sort of picture it. Maybe 6.
6 is right. And that process, that internal command and visual scan, the lecture calls it a miracle of intelligence. Our language and perception systems working together. If we don't understand that, we don't fully grasp intelligence.
That interaction is, yeah, incredible when you think about it. I do that all the time without noticing. So the current phase in AI, the age of the right way, is that about trying to build that kind of internal teamwork?
That's exactly it. It's about understanding the loops, connecting thinking, perception, and action. Look at the imagination program demo from the MIT lab they described.
Imagination program.
Yeah, an AI that can literally imagine scenarios like a ball falls into a bowl or a man runs into a woman, even impossible things like a man flies.
Mm-hmm.
And then, crucially, the AI uses its own visual system to read those imagined scenes to answer questions about them.
So it's not just recalling facts, it's running simulations.
Precisely. Internal simulations, using its own mind's eye, just like we do. That's the goal, mimicking that fundamental human ability.
That's really heading into sci-fi territory, isn't it? Amazing. To really get why this age of the right way is such a big deal, maybe a quick trip through AI history would help.
Good idea. It's quite a story. Starts way earlier than most think. Lady Ada Lovelace, 1842, often called the first programmer. And she had this amazing insight. Machines only do what we order them to do. That question still echoes today, right?
I'm still debating that one, yeah.
Then Alan Turing, 1950, his famous paper on the Turing test. But the source reminds us, about his vital code-breaking work in WWII and his tragic end. Then Marvin Minsky's 1960 paper, Steps Toward Artificial Intelligence, really kicked off the modern field.
Okay, so that's the starting line. What came next? The Dawn Age.
Right, the Dawn Age. Early glimmers. Jim Slagle's program did symbolic integration calculus, manipulating symbols like X and Y. That really wowed people. Maybe it led to some over-optimism about thinking machines being just around the corner.
Ah, the first AI hype cycle.
Pretty much. Then you have things like Eliza, the chatbot, more of a clever trick maybe, but showed how easily we see intelligence in conversation. There were programs solving geometric analogies, like on IQ tests.
Yes.
A is to B as C is to what? And early work on perception. Getting programs to understand shapes. Sometimes getting fooled by ambiguities, just like our eyes do. Plus, systems that could learn concepts, like what an arch is, from just a few examples. Early machine learning, really.
And then came the expert systems.
Exactly. The late Dawn Age. Rule-based expert systems. The big one was MYCIN from Stanford. It diagnosed bacterial infections, actually better than many non-specialist doctors for those specific infections.
Wow. Did doctors use it?
Not widely in clinics for various practical reasons, but its impact, huge. It launched 1,000 companies, the lecture says. A real-world example still running is the system managing airplane parking at Atlanta's airport. Saves Delta millions in fuel, apparently $500,000 a day.
$500,000 a day. Just from parking planes smarter.
Using a rule-based expert system, yeah. Optimizing gate assignments, taxi routes.
Incredible. What came after the expert systems boom?
The bulldozer age. This was when people realized maybe brute force computing power could substitute for, well, intelligence, at least for some tasks. Deep Blue, the chess computer that beat Kasparov, is the classic example.
Right. Didn't think like a human grandmaster.
Not at all. It just crunched possibilities, millions per second, like a bulldozer processing gravel, as the source puts it. It was powerful, sure, but it showed the limits of brute force. It lacked intuition, adaptability. That pushed researchers to ask, what are we really trying to build here?
And that leads us back to today, the age of the right way.
Exactly. Trying to integrate thinking, perception, and action. Learning from all those previous ages. Recognizing it's the interaction between these parts that matters.
What a fascinating history. Ups and downs, hype and reality checks. Which brings up maybe the biggest question, why are we still optimistic about AI? What's so special about human intelligence that we're still chasing it?
Well, the lecture pulls in ideas from paleoanthropology. Humans, anatomically like us, have been around maybe 200,000 years. But something major shifted shortly before 50,000 years ago. A key accident of evolution, maybe in a small group, possibly helped by a population bottleneck, when our numbers dropped drastically.
A bottleneck. So a small group got a crucial upgrade. And Noam Chomsky's idea, quoted in the source, is that this upgrade was, what was it again?
It was the ability to take two concepts and combine them to make a third concept without disturbing the original two concepts, without limit.
Hmm.
Think about it. That's the root of metaphor, creativity, building complex ideas, and it's tied deeply to language.
Combining concepts without limit, that sounds fundamental. So for you listening, that core ability mixing and matching ideas to create something new that's uniquely human, the engine of learning.
Right. And language has this amazing dual power. Going up, it lets us describe things, tell stories, build knowledge education, basically. But going down, language lets us direct our own minds. We can marshal the resources of our perceptual systems, even command them to imagine things we've never actually seen.
Command our perception, like
Yeah.
with the Africa map earlier.
Exactly. Or take the bucket examples from the lecture.
Oh, okay.
Imagine running fast with a bucket full of water. What happens?
Water sloshes out, my leg gets wet instantly.
Right. You just know that.
Hmm.
Did anyone teach that specific fact? Probably not. Now imagine running with a bucket full of nickels.
Ooh, heavy. I'd be bent over, staggering.
Again, you just simulate it instantly. These aren't facts you Google. They come from your internal simulation engine, your imagination. That's the human magic we often take for granted.
That ability to just simulate reality internally.
And the lecturer concludes that understanding that internal imagination, that simulation power, is vital. Vital for understanding ourselves and vital for the next leaps in artificial intelligence. That's the frontier.
So wow, what a journey we've taken. We went from defining AI with models and representations, explored simple but powerful tools like generate and test, saw how crucial perception and imagination are, traced that whole whirlwind history, and landed on what might be the core of human uniqueness, that limitless concept combining, that internal simulation powered by language.
Yeah, and the big takeaway, I think, is that this quest for AI, it's not just about making smart machines. It's forcing us to understand intelligence itself in all its forms much more deeply, both artificial and, importantly, our own. We learn more about ourselves by trying to build something intelligent.
Which leaves us and you with a final thought to consider. If we can genuinely teach machines to imagine, to run those internal simulations, to combine concepts without limit like we do, what new frontiers of intelligence, creativity, maybe even understanding could that open up? Not just for AI, but for our own understanding of what it means to be human. Something to think about until our next deep dive.